So we have already seen the Rees representation theorem, which states that if you are given a linear functional T on an inner product space V, there exists a unique W in V such that TV, which is a scalar, is the inner product of V with W for all V in capital V. Our next goal is to study how the inner product interacts with linear transformation between inner product spaces, and in order to do that, we develop the notion of what is called as the adjoint of a given linear transformation. So let's begin by considering a linear transformation between inner product spaces. So let T from V to W be a linear transformation between inner product spaces. V and W. So let W be some vector in capital W, and let's define a function. Let's define T subscript W, which is from V to R, by what is T W of small v? This is defined to be the inner product of V with W. So let's look at an example to understand what we are doing. So suppose T is from say R3 to R2, given by T of say x, y, comma z. This will be some vector in say R2. We would like to see what, okay, let's put it something x plus y plus z. It will be too simplistic. X plus 2y plus 3z, 4x plus 5y plus 6z. Suppose we have two such coordinates where x, y, z is being sent to, and we would like to define what is, so let's fix W to be, let's say this is equal to say something like 1 comma 2. Notice that W should be in capital W, right? That is what our choice here was. So fix one such vector 1 comma 2 in the target, which is R2, and let's define TW of XYZ. What was this? This was basically T of XYZ. So basically that is the vector x plus 2y plus 3z and 4x plus 5y plus 6z. This vector inner product of this with W, which is 1 comma 2, which is equal to x plus 2y plus 3z times 1 plus 2 times 4x plus, so I will write it down directly. This is 8x plus 10y plus 12z, which is equal to 9x plus 12y plus 15z, which happens to be linear functional. So notice that this is TW of XYZ. So this happens to be a linear functional on R3, which is the target. So that is not any mere coincidence. So let's observe that this function, which now I am underlining in green, which is from V to R, is always going to be linear. So this is in particular linear functional. Okay, so I should let me just prove that first. So claim TW from V to R. So we are not in the setup of the example, we are in the setup before that, where T is a map from, so T from V to W between linear inner product spaces, which is a linear transformation, and WB in capital W. TW of V is defined as the inner product of V comma W. This is the setup. So the claim is that TW is a linear functional. So like in this case, the example, it just happened to be a linear functional. It is going to be a linear functional always. So let's give a quick proof of this. So what will be necessary to show that this is what is it that we have to check? The first one is to check that if we have V1 and V2 in capital V, what is this? By definition, this is T of V1 plus V2 inner product with W. But T is a linear map to begin with. So this is just inner product of TV1 plus TV2 and W, which by the properties of the inner product is the inner product of TV1 with W plus the inner product of TV2 with W. But that is by definition. The first term is TW of V1 and the second term is TW of V2. That by establishing that TW is indeed additive. So the first property is checked. This is for all V1 and V2. For all V1 and V2 in capital V. And for C in the field of scalars and V a vector in capital V, let us see what this is. This is again T CV inner product with W, which is equal to, let me skip a few steps, write it as C times TV comma W, which is equal to C times TW of V. And therefore TW is always a linear functional, and therefore hence TW is a linear functional on V, on an inner product space V. But what do we know about linear functionals on inner product spaces? We know that by Rie's representation theorem, there is some vector W, W is already picked, so T star W now, which when you take the inner product with V will give you our linear functional. So let me just note that by Rie's representation theorem, which we proved in the previous video, Rie's representation theorem, there exists a unique vector. So let's call it T star W in capital W. So notice that, okay, not capital W, this is in capital V. Notice that this is the inner product which is being taken in capital V. So I'm not writing down where which inner product is being taken, but the context should make it clear. That's that. Let's see what so such that TW of V is equal to inner product of V with T star W. This is precisely the statement of Rie's representation theorem, right? TW is a linear functional. So there is a unique vector T star W in capital V such that if you look at T star V, V inner product with T star W, that will give you TW of V. But what is our left hand side? Left hand side TW of V is nothing but the inner product of TV with W, which is equal to V comma T star of W. So notice again, now we should be a bit more careful as usual. The left hand side, the inner product is being looked at in the inner product space W. The right hand side is the inner product in capital V. So the abuse of notation, however, is quite clear from the context and shouldn't create any confusion. All right, so we have seen an example here. Let's do one thing. Let's compute the explicit formula of T star in our case. So let me just write down here the example. I'll write this as example above continued. Let me write it like this. So recall that T of x, y, z was equal to x plus 2y plus 3z and 4x plus 5y plus 6z. And let's attempt computing what is AB. So T is from R3 to R2. So T star will be from R2 to R3, right? So AB will, let's see what AB is. AB in R2, we would like to compute what is T star of AB. And let's look at the formula just above. T star of AB will satisfy this formula. So T star of, let me write it like this. TV is, so x plus 2y plus 3z comma 4x plus 5y plus 6z. This inner product with AB is going to be equal to, what was our V? V is in our case x comma y comma z comma t star w. This is precisely the formula we have from star. Okay, what is the left hand side here? Left hand side is a times x plus 2y plus 3z plus 4x plus 5y plus 6z times b. What is this? Let's just compute what this is. This is equal to a plus 4b times x plus 2a plus 5b times y plus 3a plus 6b times z. But because it is in R3 and the inner product, standard inner product of R3 is quite familiar for us. We know that this is the inner product of the vector x, y, z and a plus 4b comma 2a plus 5b comma 3a plus 6b. But what is this? This is also equal by star, or by from here this is also equal to the inner product of x, y, z and t star w. But the uniqueness, so what is this telling us? I.e., let me just write it down clearly so that it is clear. Inner product of x, y, z and t star w, this is equal to the inner product of x, y, z. So w, let me just write down what w here is. W is a comma b is equal to inner product of x, y, z and a plus 4b, 2a plus 5b, 3a plus 6b. And this is true for all x comma y comma z in R3. And this implies, by the uniqueness, the proposition which proved uniqueness in the previous video, this proves that t star of a comma b is equal to a plus 4b, 2a plus 5b, 6, 3a plus 6b. Okay, that's good because if you notice, t star, i.e. t star from R2 to R3 is a linear transformation. Of course, in this case, we have very specifically computed it in this particular example and we obtained that. But this is a good motivation to conjecture that the map T star that we are defining in the general case always happens to be a linear transformation as well. So that is going to be the content of our first proposition. So let's state it and prove it. So let T from V to W. So did I define what T star is? Okay, so I have a definition to make before that. So before I jump into the proposition, let me give the definition of the adjoint. All this was the precursor for this definition of the adjoint. Let T from V to W be a linear transformation between inner product spaces. T star, okay, then the adjoint of T of T, which is denoted as T star, denoted by T star, is the map as defined above from W to V such that inner product of V TV comma W, which is in capital W, is equal to the inner product of V with T star W. So this is what we had. We just showed by Rees representation theorem that we can define such a map T star from W to V, and that map is called as the adjoint of T. The next proposition, which I was about to state a few minutes back, let me now state it. It states that the adjoint of a given linear transformation between inner product spaces will again be a linear transformation. So let me write it down. So let me just run over the definition for you once more. You start off with a linear transformation from V to W, where V and W are inner product spaces. The adjoint T star of T is a map from W to V, such that inner product of TV and W is the same as the inner product of V and T star W. This T star W, as we had seen, is obtained using the Rees representation theorem applied to T subscript W, which we had defined a bit earlier. Okay, so the proposition states that, so the context of the proposition is that let T from V to W be a linear transformation between inner product spaces then T star from W to V is a linear transformation. Okay, so let's give a proof of this statement. Proof. The main tool that we have to go by is this particular equality. The inner product of TV with W is equal to the inner product of V with T star W. So let's somehow use this to prove that T star is a linear transformation. So let W1, W2 be in capital W. Then let's look at what is the property that is satisfied by T star W. So T star W1 plus W2. W1 plus W2, inner product of this with a vector V in capital V. By definition, this is equal to the inner product of TV with W1 plus W2. But inner products are conjugate linear in the second variable as well. So in particular, it is additive, and hence this is equal to the inner product of, this is the inner product in W that we are looking into. This is inner product of TV with W1 plus the inner product of TV with W2. But we know that by the property of the adjoint, which we have just defined, this is V inner product with T star W1. Notice that we have now moved over to an inner product in capital V plus the inner product of V with T star of W2. And by the properties of the inner product in capital V, this is the inner product of V with T star W1 plus T star W2. Now again, both these are linear functionals. This is also a linear functional. This is also a linear functional when looked at as a function on V. And by Rees representation theorem, there exists a unique vector in capital V, which when you take the inner product with V will give you the linear functional. And therefore, by the uniqueness, this implies that by the proposition that we proved in the last lecture, this implies that T star of W1 plus W2 is equal to T star of W1 plus T star of W2. By uniqueness in Rees representation theorem. You should check the uniqueness part. You should check very carefully how the uniqueness is being used here to conclude that T star of W1 plus W2 is the same as T star of W1 plus T star of W2. Okay, we have seen the case when it is the check for whether T star is additive. Now let C be some scalar and W be some vector in capital W. So notice that we have slowly stopped any reference to our field of scalars being exclusively real numbers. That is not at all the case we are considering. There is all these statements are completely true, even keeping in mind that the possibility of the field of scalars being complex numbers is there. Therefore, if you look at T star of CW, and if you look at the inner product of this with V, this is equal to the inner product of TV with CW by the very definition. And the inner product in W, which is being considered to the right, we can take out the scalar out. It is conjugate linear, remember that. So this is going to be C bar times TV comma W, which now by definition is the inner product of V with T star W. This is the very definition of the adjoint that we have defined, and therefore this now can be brought back in by using the properties of the inner product, in this case in V, to conclude that this is C times T star of W. But this is true for all V in capital V, and hence as linear functionals, this and this both are linear functionals which are equal, and by uniqueness of the Rie's representation theorem, this gives that T star CW is equal to C times T star W by uniqueness. I'll just write by uniqueness here. You should again think over how uniqueness was used here of the Rie's representation theorem. Okay, both the checks are done. This concludes that T star is a linear transformation. So given any linear transformation T from V to W, we are able to get hold of a T star which is again a linear transformation from W to V. So you might be tempted to think of the adjoint as something like the inverse, but let me stop you right there and say that the inverse of a linear transformation can be defined only when the linear transformation is invertible. However, the adjoint can be defined for any linear transformation. So the right notion with which you should probably, so if you look at inner product of say V1 and CV2, suppose this is the case, this is, what is this? This is C bar times V1 comma, or maybe I should start here. Let me start with C V1 comma C2. This will be C times V1 V2, and this is going to be V1 comma C bar V2. So C is becoming C bar when it is going to the other coordinate in the inner product. So T star in some sense captures an analog of the complex conjugate in the language of operators, linear maps. So for linear maps, the adjoint in some sense is the correct notion of the complex conjugate that we have to consider. We will elaborate on this in a few minutes, and to do that, let's use the power of V and W being inner product spaces. If you notice, if we scroll up a bit and look at the example that we were evaluating, we did some amount of computation to come to the conclusion that our T star here is being defined in this manner. It might actually be a good point to say that if we are to use the tools of the orthonormal basis that we have, the notion of orthonormal basis that we have in an inner product space, a lot of these things might actually turn out to be far simpler. So our next goal here is to compute T star, the matrix of T star rather, in terms of the matrix of T by using the tools of an orthonormal basis. So let's fix. So let's fix beta, say V1 to Vn, and gamma, which is say W1 to Wm. So in this case, now we are in finite dimensional vector spaces. Still now, to define most of the things we defined, we were not Oh, yes, we did. So let me be a bit careful. Let's not bother about infinite dimensional inner product spaces right now. We did use Rees representation theorem to get hold of adjoint. So in the case of infinite dimensional vector spaces, we do not have a ready analog of Rees representation theorem, and we will have to do some work, if at all it exists, to talk about the adjoint of a given linear transformation. So in this lecture, let's all through assume that our inner product spaces are finite dimensional. We have indeed used it very strongly to even talk about what T star W is. So let beta V1 to Vn and gamma W1 to Wm be orthonormal bases of our inner product spaces V and W. What is the good thing about an orthonormal basis? When we have an orthonormal basis V1, V2 up to Vn, we know the explicit expression of any vector V in terms of say V1 to Vn. We know that. So let me recall that V is the inner product of V with V1 times V1 plus up to V with Vn times Vn for all V in capital V. We know that any vector, we know the explicit linear combination of V1, V2 up to Vn, which will give us the vector V. So what we will do is, let's compute the matrix of T with respect to beta gamma. So goal to compute T beta gamma, and for that we will be considering what is TV1 with respect to gamma, TV2 with respect to gamma, and so on, TVN with respect to gamma. This will be our columns of the matrix T beta gamma. Okay, but we know explicitly what this is. So this is going to be, so hence T beta gamma will just be equal to the inner product of TV1 with W1, TV1 with W2, TV1 with Wn. This will be the column representation of TV1 with respect to gamma. How about the second column? TV2 with W1, TV2 with W2, TV2 with W, oh, this is not Wn, this is Wm. After all, it's an m cross n matrix, right? Because W is of dimension m. And let's go to the final column. Final column will be TVN W1, TVN W2. This will be TVN Wm. So this is our m cross n matrix of T with respect to beta and gamma. So what is the ijth entry? Let's explicitly write down what the ijth entry is. Hence, the ij entry of T beta gamma, this is nothing but, let's go back to this matrix, check it out. The I is here, j is here. So the ith one is with respect to wi, and the jth one is with respect to vj. So this will be T vj wi. This is our matrix ijth entry of the matrix of T with respect to beta gamma. Now we know where T star is from. T star is a map from W to V, and we have the same orthonormal bases gamma and beta of W and V respectively. Let's see what will be the expression of T star with respect to beta gamma. So what is T star, not beta gamma, gamma beta, gamma beta. But we already did the hard work to show that, right? The ijth entry is equal to T star of, in this case the role of V and beta and gamma is reversed, so this is going to be T star of Wj and Vi. This is precisely the Ij entry of, if you do the same process that we did above, this is what the Ij entry of T star gamma beta will be. But what is T star Wj Vi? That is nothing but, by the definition of the adjoint, this is Wj and Tvi, and by the properties of the inner product, this is going to be Tvi Wj bar. So let's just write down what T star. So this is the ijth entry of T star gamma beta. So let's see what will be the 1jth entry. What will be the first column? 1j entry will be just Tv1 Wj bar, Tv1 W1 bar, Tv1 W. Let me write it down. The first row, for example, when I is equal to 1, this is just going to be Tv1 W1 inner product of this bar, Tv1 W2 bar, and the nth, so this is going to be Tv1 Wm. This is the first row. Second row similarly will be Tv2 W1 bar, Tv2 W2 bar, Tv2 Wm bar, and finally the last row will be Tvn W1 bar, Tvn W1 bar. So this is our matrix. So I have just written down all the entries. Let me just put the brackets. This is the matrix of T star gamma beta. And if you notice, this is just the adjoint of the conjugate transpose of our matrix T beta. Let me just note down that this is just T beta gamma adjoint. If you recall, this was the symbol we used for adjoint. Let me just write it down in brackets. Adjoint of the matrix adjoint of T beta gamma. Remember that recall that the matrix adjoint of a matrix A will be the conjugate transpose of the conjugate of the matrix. So you first take the conjugate of the entries and you look at the transpose of that. That is what is being defined as the adjoint of our given matrix. So if you notice carefully, the choice of the word adjoint for the matrix adjoint was not arbitrary. It just turns out that when we are using when we are defining adjoint of a linear transformation in the way we have just defined, and if we compute the matrix of T, and if you look at the matrix of T star, it turns out to be the adjoint of the matrix of T. So these notions are clearly well motivated and rightly defined. So note again back on the similarity of our notion of T star to that of taking conjugates of a complex number. If you notice that if T is a map from C to C, the conjugate transpose will just turn out to be the conjugate. So here, when the case of one-dimensional complex vector space to one-dimensional complex vector space is considered, and if you look at a linear transformation, the adjoint is just going to be the conjugate. Right, so this is the right notion which generalizes the idea of the complex conjugate. Maybe we should just go back to the example that we were considering. If you recall, this is again, I'll put a continued to remind you that we were already looking at this. This is, what was this? This was x plus 2x plus 3y, 4x plus 5y plus 6z. And with respect to the standard basis, so let beta and gamma be the standard basis of, let's just pick R2 and R3 and R2. Notice that such a linear map could also have been defined between C3 and C2 as complex vector spaces, but let's focus on R3 to R2. And then what will be the matrix of T beta gamma from R3 to R2 with respect to beta and gamma? This will just turn out to be equal to, let's see, what is 1 0 0? That is just going to be equal to 1 comma 4, 2 comma, okay, this is x plus 2y, 2 comma 5 and 3 comma 6. And what will be the conjugate transpose? The adjoint of beta gamma will be the first the transpose, so 1 4 2 5 3 6 and the conjugate of all this, but these are all real numbers, and hence this is just going to be equal to 1 4 2 5 3 6. So this is going to be the matrix of T star. So this is our T star with respect to gamma beta. So let's see what is T star of, say, A comma B. This is just going to be multiplication by this matrix with respect to the standard coordinates. This is going to be A plus 4B, 2A plus 5B, 3A plus 6B, which is the column representation of T star AB, which we have already computed. Let's just go back and check. A plus 4B, 2A plus 5B and 3A plus 6B. So yeah, so it's a cross check of what we have done, and it is indeed the case. Let's look at one more example just to be in just to check that this is let me just call it a problem now, so in this week and the next, the problem session is kind of integrated into the lectures. So let me just call it a problem. So the problem is that let T from Cn to itself be a linear operator be given by T of Z1, Z2 up to Zn. This is defined to be 0, Z1, Z2 up to Zn minus 1. So the problem is to compute T star. So there are two ways to go about doing it. One is to check directly what the answer would be, and the second option would be to compute the matrix of T and look at the conjugate transpose. So let's do both. It's not a complicated problem. So let's see what T star of, say, W1 to Wn, this is what we are interested in. Oh, but yeah, so basically this will be a vector in T star will be from Cn to Cn. So let's see what will be the inner product of Z1, Z2 up to Zn and T star of W1, W2 up to Wn. Let's see what this is. By definition, this is just going to be equal to T of Z1 to Zn comma W1 to Wn. But we know explicitly what our T is, which is equal to 0 Z1 up to Zn minus 1 comma W1 to Wn. And we know the standard inner product in Cn. This is just Z1 times W2 bar plus up to Zn minus 1. 0 times W1 bar is 0, so I didn't write it, plus Wn bar. But what is this? This is just the inner product of Z1 to Zn with 0 comma W1 to Wn. the inner product in Cn is quite straightforward. So maybe I'm making a mistake. Let me be a bit careful. Yes, it is a mistake. So this is Z1 to this thing and W2 to Wn comma 0. This is precisely what we are looking at, right? If you carefully observe. But this is equal to this. Now again, by the uniqueness in Rie's representation theorem, this is true for all Z1 to Zn. So let me just note it. For all Z1 to Zn in Cn. And this implies that T star of W1 to Wn is equal to W2 up to Wn comma 0. So in some sense, what is happening is, if you consider the right shift, this is in some sense the right shift operator. Of course, we are not doing it strictly, the Zn is being thrown out, so I am not calling it the right shift. It is like the right shift operator, and the adjoint is giving us something like the left shift operator here. Okay, so that is one way to compute T star. The other way is to compute the matrix of T. So let beta and but beta be the standard basis of Cn. Standard basis, if you recall, is E1, E2 up to En, where Ei is having 1 in the ith position and 0 elsewhere. So let beta be one such standard basis. So let's try to see what is the matrix of T with respect to beta. Well, it will be T of 100 with respect to 100. T of 100 is 0100, which is just 01000. T of 0100 will be 00100. After all, this is with respect to the standard basis. The n minus 1th column would be 0000 and 1 in the nth one, and the final, if you notice, T of En is going to be 0 because it has only 1 in the nth coordinate and 0 elsewhere. By shifting it to the right, it's being thrown out. So this is going to be the matrix of T with respect to beta. The conjugate transpose, the adjoint of T beta beta, in this case the entries are real, so the conjugate will be the same. It's just going to be 01000, 001000. The second last one will be 00001, and the final column would be 000. And if you multiply W1, W2 up to Wn with this, you are precisely going to end up with this particular vector. So yeah, both these obviously should be giving the same vector, and yeah, we have just cross-checked that it does. Okay, let's do a couple of problems more. Okay, let's get more familiarized with the notion of adjoint by computing the adjoint explicitly. So let T from V to W be a linear transformation, be the linear transformation. Okay, so to talk about T, let's fix. So let V0 be in capital V and W0 be in capital W, be fixed vectors. Where are these fixed vectors? These fixed vectors are in an inner product space. And we can define a linear transformation T from V to W by TV is defined as the inner product of V with V0 times W0. You should check that this is indeed a linear transformation from V to W. Compute T star. Of course, multiple approaches. Here I think the first approach might be better. Let's check. We would like to compute what is T star of W, right? Let's do the standard trick. Let's look at the inner product of a vector V with T star of W. This is just going to be the inner product of TV with W, And we know what TV is explicitly. This is just the inner product of V with V naught times W naught into W, which is in particular inner product of V with V naught times W naught with W. That's interesting because both are scalars. The first one is an inner product which happened in V. The second one is an inner product which happened in W. Nevertheless, both are scalars. We can pull the scalar in by using the linearity in the first variable. This is going to be W naught W, or let me be more careful. This is going to be, what do we want? We want T star of W, right? So this is going to be V and W naught comma W bar times V naught. So let me just go back and see if there is any mistake. There is a good possibility that there is a mistake. So this is TV comma W. TV is V comma V naught times W, and this comes out as a normal one, and this goes in. Yeah, all this is right. So hence T star W is equal to the inner product of W0 W bar, which is the same as W0 times V0. So this is the explicit expression for T star. So let me do one more problem before I conclude this video. So the problem is the following. Suppose V is an inner product space, T from V to V be linear transformation, linear operator on an inner product space V, and suppose U is a subspace of V. Yeah, then prove that U is T invariant if and only if the orthogonal complement of U is T star invariant. So if you recall that a subspace U is T invariant if for any vector U in capital U, TU is also in capital U. Okay, so there are two directions to prove. So let me just prove the forward direction. So suppose U is T invariant. Let's prove that T star U orthogonal complement of U is T star invariant. So let's start with some vector. So let U prime be in the orthogonal complement of U, and let's see what is the situation of T star U. We would like to see that it is in the orthogonal complement of U, right? So for U in capital U, consider inner product of U with T star U prime. If we show that this is equal to 0 for all such U in capital U, then we would have proved that T star U prime is in the orthogonal complement of U as well, right? Okay, but what does this mean? What is U? This is a comma, this is not U1. U and T star of U prime, this is just equal to by the property of the adjoint TU and U prime. So recall that U prime belongs to the orthogonal complement. U is in capital U and capital U is T invariant. Since TU belongs to capital U and U prime is in the orthogonal complement of U, we have TU and U prime. When you look at the orthogonal inner product, they are orthogonal, it will give us 0. This implies that U T star U prime is equal to 0. But that's true for all U in capital U. For all U in capital U. This implies that T star U prime belongs to the orthogonal complement of U. And hence U orthogonal complement of U is invariant under T star. To prove the converse, Let me just say that the orthogonal complement of the orthogonal complement of U is equal to U, and the same proof works there as well. So to prove the converse, this was an assignment problem. I hope you have done it. To prove the converse, use the fact that U orthogonal complement of the orthogonal complement of U is equal to U, since U is a subspace, and hence apply the and use the same argument above. Alright, so let me stop here.